The Rockies are right over there. Don't just go to the conference. Go and see the Rocky Mountain National Park. Go hiking up at Bear Lake or something. Don't do what I did, which is just to come for the conference. Go and see the area.
Hello everyone, good morning. My name is John Bandela, and I'll be talking about Beyond Struct, metaprogramming a struct replacement in C++20. Just a few disclaimers. This is not an official Google library, and these opinions are my own and are not reflective of overall consensus or anything at Google. All right. So let's look at something that we're all familiar with, our struct, right? And we'll just look at it without any member functions, any constructors, and just see what it is that we can do with it, right? So we can have a struct, and then we have, just make it simple, a person, right? Has an ID, a name, and a score. Maybe you're writing a game or something like that. So what can we do with it? So one of the nice things in C++11 is we can specify a default value for a field, right? So we can say int ID equals 1. That way when I construct it, like a default construct it, it'll have some defined value instead of some undefined value that I don't know. The other thing we can do in C++20, one of the nice things we can do is designated initializers. We can specify, hey, I want this field to be the ID to 1, the name to be John. I can do that. The final thing I can do is I can access the members, right? I can do p.id, I can set it, I can read from it. So these are what I can do with a struct. What can't I do with a struct? Well, unfortunately, we don't have static reflection. People here in the audience, I'm sure, know better idea of when we might get static reflection. I don't think it's C++23. We don't have static generation, which is not just looking at a struct, but like, hey, can we generate a struct? And then two minor things, like no required members, and designated initializers are required to be in the order of declaration. That's a C++ thing, not a C thing. So I don't know if when that may be lifted. All right. So let's look at static reflection. There's been talks here at CppCon about how you can actually get some type of static reflection using or abusing the structured bindings. And there's something called magic get, which will get you a tuple out of a struct. However, you don't have the names of the members. There's no way to get that. So if you want to write, say, for example, something that will automatically read to and from JSON, you can't go there. Like you had to use some macros or provide some other information about, hey, what are the names of these fields? All right, and there's no generation, right? We can't create a new struct with names. Example, because it's familiar, JSON, right? Like if we had a compile time JSON string, can we say parse this and give me back a structure? We can't do that. And there's a minor thing, no required members. We can't designate that a member must be specified on construction. Like, hey, you had to provide a value, a parameter for this member. Like we could there's a way to hack around it by we can write ourselves a required template that, deletes the default constructor and say, hey, we can just wrap our type in there. But the problem is in C++, there are no transparent types. And once you start trying to write a transparent type, you'll run into all these edge cases where it works, but it doesn't work. That's a hat tip to Titus, who keeps on reminding me of that. All right, so let's go beyond struct. So we're going to use C++20, and like I said, every game has to have a set of rules. We'll say no macros. All right, sound good to everybody? Okay, anybody know what this is from? Yeah, so Jurassic Park, Dr. Ian Malcolm, and the quote is, yeah, but your scientists were so preoccupied with whether or not they could, they didn't stop to think if they should, right? So, the advice is before you do something, just because you do it doesn't mean that you should do it. However, for this talk, we are going to completely ignore that advice. All right, so, whether or not this T-Rex here gets out into the world, that's up to you. But, we're going to ignore compile times, we're going to ignore compile bloat, we're going to ignore error messages. We're just going to see what can we do. All right, so let's get started. So how do we define and access members? So what we do is we're going to create this struct called metastruct. And we specify it using these template called members. And I'm ignoring all namespaces and everything. So we have a person that we define as a metastruct, right? And a member, and we have an ID and a name. And we can get via tuple, except instead of providing an index, we provide a string, and we can set it and we can access it. So for this talk, I'm going to cover it in sections as we gradually build up. And so because they kind of build on each other, if anybody has any questions, please interrupt me, and then we'll get stuff straightened out. Because some of the techniques, if you don't get at the beginning, then you're going to spend the next 40 minutes wondering what's going on and won't get out as much. So any questions about this so far? So how do we do that? So one of the nice things in C++20 is that we can have strings as template parameters. And that's because of a generalization of being able to provide class types as non-type template parameters. And this is basically adapted from the paper, which has an example of this. I removed the template on the char type because I'm only ever going to be using a char for this. And the magic incantation here is if you look here, is the spaceship operator that's defaulted, and we don't have, and it's a structural type, we don't have any pointers or references. So with the default, the compiler knows how to compare equality and inequality and all that, and it can use that to see if two templates are the same. So we have this fixed string, and it's basically, read the paper, copy and paste. And at the bottom, we have a class template argument deduction guide that tells us, hey, whenever you see a string of, of length n, create a fixed string of length n-1. All right, so what does our metastruct look like? So we have this type called members, which takes fixed string, and we have a tag that's a non-type template parameter called fixed string. And because we have CTAD, the argument deduction for the template, we don't have to provide an n for it. And we just have a little accessor tag and type def for element type, and we store the value. And for metastruct, we just take a parameter pack of members and inherit from them. So how do we actually access it? So what's really cool about C++ is C++ overloading is crazily powerful. So what we can do is we can split it up into two parts, like a get Impl. So we have a template function that has fixed string as the tag and the type name. And then we just say, hey, and there's overloads for const ref, r value ref, but we'll just do the regular L value ref. And we have get Impl, decal type auto, and we say, hey, can you match a reference to member tag? Now the trick is, then we have a function that calls that called get, that we take a metastruct in, and the trick is we explicitly specify the tag. So this get Impl will automatically be resolved to any member that has that tag. And since they all inherit, since metastruct inherits from all the members, any member that matches that tag will get passed into get Impl. So if you don't have a tag, you get an error, or if you have more than one tag of the same type, you get an error. All right, so now we've got defining and accessing members. Any questions? So let's move on. So how do we construct this, right? It'd be nice to be able to provide arguments. So what we can do is we can say, okay, we have this arg that we provide the tag to, and we say equals 1, and we can pick Juan or John, and then we can get it like we do it. And it doesn't matter if what order we put them in. No matter what order we do, they will just work. How do we do that? All right, so let's define arg. So arg is, I guess, a nebloid. You can see that there. It just has an operator equal, and it constructs and returns a tag and value. And tag and value is just a simple struct that has a tag in the template type parameters, the non-type template parameter, and it stores a value. And then we just create a const per arg template variable of that. Right, so that accesses R. So when you have that, we have an arg tag, and then we do operator equal, we can construct a tag and value object. And then for metastruct, what we had to do is instead of directly inheriting from members, we need a little helper called metastruct Impl. And what we do is we take all those tags and values, we'll take a parameter pack, and construct a Parms object out of them and pass them to our parent, which is the metastruct Impl. And all Parms object, again, is we just inherit from all the tags and values. And metastruct Impl members, it inherits from all the members, and its constructor receives the Parm object and passes the same Parm object to every one of its members' constructors. Now the magic happens down here. Each member constructor, right? Remember the tag is fixed and the type name is, and the T is fixed for the type, but we take we template it on an other type. So as long as it has the same tag, we don't care what type it is, as long as it can convert, or else we'll get a compiler error. And the parms will object slice down to a tag and value. So this is one of the few times where object slicing in C++ is actually something useful that we can take advantage of, right? And then we can overload it and pass it in. So this is construction. Any questions about this? Go. Because the order is because we pass the same Parms object to every member. So we construct the Parms object that inherits from all the members, and we pass that object to all of them, and it doesn't matter what order it is, as long as each one will basically, kind of like a gyro thing, right? Each one will slice off the member that it needs from the Parms object. Go ahead.
So in your metastruct Impl constructor, you're moving the Parms.
Right, so what we do is we do a move on it. Remember, move doesn't actually move, it makes an R value graph. So when we slice, we actually move out of the slice to construct it. Any other questions or great questions? All right, so we got construction down. All right, so we can construct. Okay, what else do you want to do? Default initialization, right? So non-static data member initialization, we'd like to provide some defaults, right? And we'd be tempted to say, hey, we can have non-type template parameters. Stuff in C++ is tongue twisty. And we can't just add, we'd be tempted to add it just as a template parameter. Say, hey, we got non-type template parameters, but we can only put in some, and we like stuff like std string in there that don't have it. So what we can do in C++20, it allows us to actually use a lambda there. So what we can do is, person, and we can say name, the default value is John, return John. So so the lambda can be passed in, and then we can return any value that we want out of it, right? So we say return John, that's our default value, and then person, so the name will be John and the ID will be, in this case, it actually turns out to be 0. So how do we do this? So what we do is we create a little function object type called default init that takes a type name, and it has an overloaded function call operator, and it just checks, is it default constructible? Return a default constructed value, otherwise, don't return anything. And then for a member, all we do is we add an extra defaulted non-type template parameter, and we say, hey, for default construction, just call the init on it. Any questions about this? All right? So we've got default initialization with a constant. All right? However, we may want default initialization with an expression, right? So, sometimes we want what the default value to be dependent on what the other value is, on what the other members of the struct are. So the way we do this, we take a lambda that takes a self parameter. So look at score. We decided, hey, score should just be ID plus 1. So what we do auto and self, and return get ID self plus 1, right? So we can have both types of lambdas in there, right? We can have one that just says, hey, I just want to return a abbreviated lambda, so I can just return like a constant or some value, or else I can actually use what's passed in self to actually calculate it. All right? So go ahead. Is there a question?
Why are you getting the ID and
Adding one?
why are you getting the ID there?
Oh, what I want to do is I want to say, hey, score equals ID plus 1 is what I do in the struct. So this is the way to do it in here. So we say, hey, whatever the ID is, and I just add 1 to it. So if an ID of 1, my score would be 2. Just that.
There's a question online.
Oh, go ahead.
Are we ever going to get, quote, normal member access?
We will, unfortunately at this time, we can't get normal member access. This is the best we can do with the get tag. All right, so how do we do this? So what we do is we have, add a constructor to member where we take a self, a templated self parameter, and we pass it to call init for self, right? And call init, we use concepts, and we overload saying, hey, what does it return? Does it how do we call it? Do we need to pass a self in or not? And we do the appropriate thing based on the overloads, right? And then for the metastruct Impl constructor, we just pass in a this. So a reference, dereference this, that provides our self, and then we can pass it to each of the members, and they can actually get which ones they want. So now we have default init with an expression, right? And now let's do optional arguments, right? So first of all, we've either been all or none, right? We needed all the parameters, or else we needed, none of them. We either default constructed or we provided all of them. What we'd like to be able to do is provide, some are default, and some are actually, we provide. For example, person, we provide arg ID equals 2, and the score and the name will be default constructed. And that can be, we specify that at compile time. However, there's some instances where we don't know if we have a value to provide. An example would be like a JSON parser, right? Like you're reading it or deserializing from JSON, it doesn't have that field in there. You'd like to say, I don't have that field, can you just put in whatever default value we had? And we change it so that like if you pass in an optional of whatever type that is, it'll use that, providing either the default for if it's not there, or else the whatever value's in there. So how do we do that? So what we do is we add an overload, right? That takes a self and a no conversion type. And then we add the optional one below, so 2 ones. But the more interesting one is the one that takes the no conversion. And what we do is no conversion, all it is just an empty struct. And in Parms, we add a no conversion operator to that, right? So if you remember when before, the metastruct Impl passed the Parms object to each of the members. So if the tag matches, it'll get sliced off, right? If none of the tags match, this conversion operator will kick in and convert it to no conversion, and then it will call the constructor that takes no conversion, and we will be able to default initialize. Any questions? So now we've got optional arguments. All right? The other thing is required members, right? It doesn't make any sense to have ID and name as default, right? There's no good real defaults for an ID. Like you'd like to require them to provide it If not, provide like a compiler thing. But the other stuff, we'd like to be able to be optional. So all we had to do is, required, we just make it an empty lambda, something that returns void, and change our call init. So if it gets called with something that returns void, we just static, we can't do a static assert false, but we just do an expression that says false and gets, hey, required argument not specified. So at compile time, we can say, hey, you specified an argument for ID. All right. Any questions so far? So let's go on to the mean. How do we do reflection, right? Like, what would we like for reflection? So we can have this meta struct apply, and we pass in a lambda, and one of the things that came with C++ 20 was we can do like regular, more familiar template syntax for generic lambdas, and we just do this type name parameter pack m, and those pointers are all null pointers. The pointers are there just as an easy way to specify just what the type is. And then we can say, hey, these are the tags, right? M tag and SV converts it to a string value. So we can have something that prints out the string, all the values of the tags. Or if we have an object, we can have something that prints out the tag and the value, right? And here we're just, we can use our fold expressions a la C++ 17 to do it for every one of the members. So now we can actually enumerate all the names and the types. So how do we do the changes? Well, for fixed string, we add a constexpr string view function SV that just constructs a string view from the data. And for our members, we just add some accessors like, hey, we can add the tag, we can access the tag, the init, the element type, and we have what the value is. And then we write the metastruct apply. For the object version, right, we can take a metastruct impl, which has all the members in it, right? We know the types of the members, and we just static cast to the base object members the structure that was passed in, and then we've got a reference to each of the members that we passed to the lambda. For the type version, where we don't have an object, so we use partial template specialization, and we do the same thing. We basically construct null pointers for member star, and we pass it to the lambda. Any questions about either of these? Okay, so now we've got reflection. All right, and some other features I will go over, but I won't actually cover the implementation like we did. Because from the implementation, you should have gotten an idea of like how this is going. Any questions so far on the stuff that we've done the implementation? All right, so let's do some other features. We can do subset conversions with this. So we can say, hey, if I have a metastruct whose members are a subset of some other struct, I can actually directly convert. So I've got a person, right, that's got the ID, name, score, and I've got a name and ID, say, that says just has name and ID. I can actually convert from person to name and ID. So this is basically kind of like generalized slicing. Oh, how many know we have attributes in C++, right? Like we can put an attribute on a thing. How many of you, there's no way for you to query what that attribute is at compile time, right? That could actually be useful for doing stuff, right? Like, there's stuff that we have that's, say for serialization, we want to specify, hey, how should you encode it? We can add attributes. So let's add attributes to our metastruct, right? So let's say we have an encoding, right? And for integers, like, we can encode either fixed or variable, right? So 32-bit integers, like there's the law of small numbers. Most numbers, especially IDs, most numbers are small, and variable length encoding can actually save you some space because, hey, most numbers are small, so we use fewer bytes to encode that. However, if we know that, hey, these are actually spread out, we may have a bunch of large numbers, we can just use a fixed size, and at the higher end, we save some space, right? So we say, hey, the ID, we want to specify that encoding that it should be variable. And so we say arg, and after that we do we do braces, and we say arg encoding equals encoding variable. And then we can go down here, and we can say, hey, give me the attributes for the ID field inside person. And we get a context for attributes. And then we can query, does it have an encoding attribute? And what's the actual encoding attribute? If it's variable, we can say, hey, the encoding was variable. Otherwise, we can say, hey, we can say the default encoding is fixed, and this is all happening at compile time, based on what we specified. Anybody want to guess what we use to represent the attributes? So, for the attributes, we need to be able to specify them, we need to query them, we need to do all that. So, hey, why don't we use metastruct there? So the reason we avoided circular dependency is because partly through the magic of partial template specialization. So the default value is one with no attributes, right? So we can declare the metastruct above the member since we don't have it, and for the empty, just specify to an empty struct. And then when we actually have members, by the time we have members and we're adding it, the rest of the metastruct has already been defined. So that's how we can kind of get around that circular thing and, code reuse. So I put a metastruct in your metastruct. All right, so we have a T-Rex, right? Like we have this thing. It does give atrocious compiler messages, like you say, car with all the ASCII values of whatever you typed in, and you try to figure out like which one did you do wrong, which one did you forget. But, and I think I had the compiler completely die on me a couple of times too when I was trying something. So it is this. What can we do with this? What applications do we have? We can actually kind of use this for named arguments, right? So let's say subster. So subster in C++, in the standard library, right? It has an offset and a count. The count is kind of the default value is like this special value, like std endpause, right? And we have a default value because, it really should default to, hey, whatever the size of the string is minus the offset, right? So we can write our own subster thing where the args, right? So we say, hey, we require a reference to a string. That's required. The offset defaults to 0. The count will default to the size of the string minus the offset, right? So then in our subster down here, we just say, hey, we call it good subster, and we've actually passed in correct things without the magic constants, right? Like we're actually passing in the correct args, the correct offset and the correct count, and we can specify, hey, we get all of it if we just specify the stir. We get the first part if we specify the count. We get the second part if we specify the offset equals pos plus 1. So we can specify count, offset, neither, but we do have to specify stir. And we can specify them in any order. And we can make stuff required, and we can have default arguments as well. So you just had to wrap it in a curly brace.
We have a question online.
Yes.
Did you consider using a tuple for members instead of inheritance? And if so, what were the trade-offs involved?
Using a tuple for it?
Yes.
I did it mainly, I wanted to minimize the machinery. So the inheritance, at least for me, it seems simpler to do and a little bit less overhead, and the error messages, were likely a little bit better when something goes wrong. And the inheritance also enables all these nice overloading tricks that I did with no conversion and and explicitly specifying the tag and doing the object slicing, which would have been much more difficult to do with tuple. Thanks for the question. So the other thing is, moving on, is array of structures versus structure of arrays. So I think this is big in game programming, where you want to have stuff efficient. For example, we've got person, right? So ID string name, this is the traditional way. We have a struct person, and we want to store them as person array of structures. We just put std vector person, right? And we can store them and access them. The other way of doing it is as a structure of arrays. So we have persons, and each item is an individual vector. So we have a vector of int for all the IDs, we have a vector of string for all the names, and we have a vector of int for all the scores. And persons, and we call that persons SOA. Why would you want to do that? So let's say, look at memory layout, right? So let's say memory, we're going from like left to right and then wrapping around, right? So if you look at how the array of structures is laid out, right? We have ID, name, score, ID, name, score, ID, name, score, right? And versus the other way where you have all the IDs together, all the names together, all the scores together. And if you want to like search for like, say, what's my max score, right? If you're doing the array of structures, you're jumping around in memory, right? From one place to another. If you have them all together contiguously, you have more efficient cache usage, and you can also do stuff like use SIMD to process like, 4 or 8 scores at a time and do all the tricks and take more advantage of the hardware that your computer has. Unfortunately, the downside is you kind of have to do this manually, right? Like if you want, there's no way that we can access those names. So what we can do, I won't go over the implementation, is we can actually, because we have access to the meta programming and we can generate the names, we can write ourselves an SOA vector, right, person. And so we can push back, like we can push back a person just like we normally would, right? If it was a vector of person, right, push back. We can actually index into it. We can actually get a whole person back, except we get a person ref, right? And a person ref is basically a person, or whatever, we can transform it from whatever the types is to depending on if you're constant or not, either a constant or a non-constant reference. So we could have, person ref would have ID, int, ref, name, string ref, and so on, right? So then we can, process it in the same way. We can like get the name just as we would from a person. The other thing we can do is we can get ourselves a span, right? We can have access to the vector, the contiguous memory where all the scores are stored. So we can get std span int scores, get the score, and then we can process them. So this enables us basically by having the ability to introspect and to reflect and to be able to also generate the names on the vector side, to basically write an automatic implementation of SOA vector that preserves names, right? The other thing we can do is duck typing for structs. We may have a function that doesn't care about the type of struct, but just the names and types of the members. And we can get duck typing in C++ using templates. For example, we have display person. We take person as a constant ref, and we say, hey, the person has an ID of ID, name of name, score of score, right? And we don't really care what the actual type is, and we don't care about the order, right? We just say, do they have a name? Do they have an ID? Do they have a score? So we can do this. The downside is this is a template function, right? So we can't do separate compilations. We can't just have a declaration and put the definition somewhere else. It has to be there. So this is how we can call it, but again, this has to be inline definition. Right? We can't use separate compilation. With metastruct, what we can do is we can say person ref and say name was a string view, ID is a constant int ref, score is a constant ref, and we say display person ref, right? And we can get the ID, the name, and the score. And the thing is, this is actually not a template function. This is a regular function that takes a type, and we can just put a declaration, we can put it in a header, we can put this in a separate compilation unit, we can put it in a library, and it will work. And we can have different persons, right? Like different order, my person meta, your person meta, you may actually have even extra fields, but as long as you have ID, name, and score that are int, ID is an int, score is an int, and name is a string, I can pass either one of them to your function. It's kind of like type erasure for structs. And the efficiency is just accessing the references a la std tie would do. So you can use a non-template that can be separately compiled. The order of the members, extra members doesn't matter. As long as the struct has the name and the convertible types, it can be passed to the function. All right. And when you're in the end, any questions so far? All right. Then the other thing we can do is generate metastructs from compile time strings. This is just an example. I haven't tried implementing. I'm not enough of an expert in regexes to do it, but this is from Hanna Dusakova's compile time regular expressions, right? This is an example from that. We have a date, which has a string view of year, month, day, and we have extract dates, and we do a match. We get a tuple back that does, that does the regular expression and returns out the matching capture groups, right? And then we can construct it and return it. So one thing you could do with this, like I said, I haven't implemented this, is regex actually has the concept of a named group, right? Of a named capture group. So you specify it, it's highlighted using question mark, angle year, angle month, angle day, and you can have a date metastruct, and this match could actually construct the date type for you directly without you doing anything. So you just return, null opter group, and you can even have it, return optional, and then you just return the CTRE match.
We have a question online.
Yes.
Would you get compile time errors if the string template parameters don't match?
You would.
When duck typing, for example?
You would. If the string template type parameters do not match, you will get a compile time error. Right now it's a very ugly compile time error, but you will get, it will stop you. You will get it. And same thing here, if you misspelled your thing, like you put like MON, you forgot MNTH or something like that, you'd get a compile time error on this as well. And like I said, the order would be the correct order, right? Like if, in your date you had day first, day, month, year, or, the American style month, day, year, right? Like whatever you did, you'd still get them in the correct order because the names are what matters, not the order. All right? And then the other thing you can do is SQL. There's parameter types, there's field names, and you can do that, but that is literally a talk for another day. Come back tomorrow if you're interested. I'm talking about how you can use these techniques with SQL at compile time to do that. This is the link to the GitHub that has some of these stuff. There's a CppCon version. It's got like copies of as we slowly develop, and I'll have some time for some questions. Questions, comments, anything you might want to say. Thank you very much for your attention. Go ahead. I've been thinking about it for a while. I originally started with like a C++ 17 version. There's a wonderful hack where you can do convert like a name of a type into a string using like a pretty function, and there's a way to do it also in Visual C++. And you can actually convert that. So I had one type where instead of names, you had like, you just had these tag structs and do it. But once I got it, like I've been working on it probably for several months off and on.
If you have a question, please go to the front of the auditorium at the microphones. We also have a question online. The machinery behind all of this is extraordinarily heavy duty. Is the compile time good enough for anything beyond a small number of simple structs?
1 second. Yeah. This is like whether or not you should, right? The machinery is behind it, right? But, computers get faster, and this is more of a way to explore potentially what you could do. Like in some personal projects, I have used this with like SQL because it's really nice. Like to be able to like query like SQLite and stuff like that, not have to deal with manually manipulating the types and names and stuff like that. But yeah, probably with this, compile time would go up. There'd probably be compiler bloat because they're not doing it. Like I said, the compiler errors are atrocious. This is more of a thing of like, hey, you can do this, not, hey, go adopt this into your code base tomorrow.
Is this on? Okay. Kind of an interesting talk. But since we're kind of totally off the rails and anything goes, have you thought about what adding member functions to this meta struct might look like?
So one thing I did play with in a previous version but then got rid of is I actually added like where you specified the member types, you could specify auto underscore and it would deduce it. Then doing that, you could actually have a lambda that you could stick in there. And with some machinery, you could probably make it look like member functions. The other interesting thing is 2 years ago at CppCon, I did a talk with like using types as the tags instead of strings and using that for like doing polymorphism in virtual functions. So you could probably do something like that. You could probably even use strings for that. And I know other people have looked at, I think Louis Dion did something with Dino like that. And, so you could probably have something like this where, both your polymorphism and your structs are all, meta something, meta programmed.
Thanks.
Thank you.
We have a question online. Is there a way to get compile time errors for wrong field names? For example, foo.wrongnamey fails, but we'll get angle brackets, quote, wrongnamey produce a compile time error?
Yes. Specifying get with the wrong name produces a compile time error. Like it is a compile time. Like if you typo it or you misspell it, you will get a compile time error. Go ahead.
Do you have thoughts on how to make your struct layout compatible with regular structs, with packing and things like that?
Yeah. One thing I was thinking about is potentially you have this type, right? You specify the struct, and maybe you have another template that basically, like packed or something like that, that takes this type and returns something with the same fields, but is packed. I don't completely have the implementation of the accessing, right, with like, with the layout and especially with the conversions. One thing is, because it's all inherited, we may be able to take advantage of like empty base class optimization for types that are that don't have any for empty types where we don't store the value. We could just return it or have some static value since it's empty. Like all the instances are the same. Right? You can't really manipulate anything. Potentially, you could probably do like similar to the empty base class optimization, like automatically with this, with some meta programming.
Could you go into a little more detail about how you're able to automatically convert from the traditional primitive struct in between that and your meta struct?
We're not converting between primitive struct and meta struct. We're converting between different types of meta structs. Yeah, you probably had to like write yourself a wrapper. I think you may be able to. I've thought about how do you convert that. There's no way to do it automatically. One thing I did think about is you could probably use and abuse like something like magic get, and as long as you specified like the names of the fields, and then you passed in the reference to the regular struct, then you could probably convert it to something like this, but you'd have to manually somehow specify the names of the fields. Go ahead.
So I missed the beginning of what you said, but at one point you mentioned move from and slicing.
Yes.
So I'm wondering, is that guaranteed? So if you say have a move only object that you inherit from and you have a forwarding, like you forward to the base constructor, are you guaranteed that that slicing, that whatever's passed in is still going to be valid at the end?
I believe so, because it's just calling the constructor, and it's a move constructor from there. So, but I'm sure there's probably a bunch of other people in the room who probably know the standards better than me, who could correct me if I'm incorrect.
We have a question online.
Uh-huh.
Have you used Metastruct to actually parse JSON?
I have not used it to actually parse JSON. I have used something like that to try to pull out stuff out of SQL. That's what I do next time. And I have tried to do something similar to try to a hacky parser for like protobuf strings to generate something like that. But I haven't used, I haven't actually written a JSON parser for this, but just because, I'm sure it's doable, I just haven't done it.
We have another question online. If you were to combine this with concepts, would that just be done to restrict the types you could add to the metastruct? Would there be any use to specializing different metastructs?
I do use concepts in the implementation, like the init, and then you can use concepts to the call init, and then you can use concepts to like kind of give you better errors for like when you pass in incompatible types, like make sure they're convertible to in the constructors. You could probably do the concepts. I just haven't thought about like what kind of restrictions that you would have on it. Yeah, but that is an interesting thing where you could have a templated metastruct that uses concepts to do that, but I just haven't explored that at all. Any other questions? Well, thank you very much for your attention. And like I said, if you want to see it for SQL, I'll put in a plug for my talk tomorrow on that. Thank you again.